Hello everyone. Today we're going to look at another interesting topic, waves and particles. This is an introduction to quantum mechanics. Here's what we're going to learn today. How 19th century physics led to contradictions involving blackbody radiation, the photoelectronic and compton effects, atomic spectra. So these were the problems in early 19th century physics. Then Planck, Einstein, and Bohr resolved these contradictions. We're going to look at how they resolved this, how beautifully they resolved these contradictions with the quantization hypothesis about role of the Planck constant H and the particle aspects of light, how to calculate photon energies and wavelengths, how to determine electron transition energies and the associated wavelengths in the Bohr model of the atom, to explain the uncertainty principle and the wave-particle duality. So these are the contents of today's lecture. Let's get started. First, blackbody radiation. A perfect absorber of electromagnetic radiation is called a blackbody because it absorbs all light and thus appears black. So the blackbody absorbs all the light, so it looks black. When black body is heated, it emits blackbody radiation at a range of wavelengths. Blackbody radiation has the following characteristic. The radiated power is given by the Stefan Boltzmann law. Stefan Boltzmann law here. P equals sigma AT to the power 4. Sigma is this constant. Sigma here is Stefan Boltzmann constant. The radiation peaks at a wavelength that's inversely proportional to the temperature. This is called Wien's law. So lambda peak times T is 2.898 millimeter Kelvin. The distribution of wavelengths depends only on temperature, not on the material of which the blackbody is made. So this is a schematic view of the blackbody. So incoming radiation is completely absorbed and it's not reflected. So that's why it's called blackbody. But there was a problem here. Ultraviolet catastrophe. Classical physics predicts that a hard object should emit electromagnetic radiation of all wavelengths, with the amount of radiation rising to infinity as the wavelength approaches to zero. One measure of radiation is radiance, which gives the radiation per unit wavelength interval. Classical physics shows radiance approaching infinity at short wavelengths. This impossible result is called the ultraviolet catastrophe. Contrary to this, experiments show that radiance peaks at wavelengths that get shorter with increasing temperature. So, in classical theory, as the wavelengths get shorter and shorter, the radiance gets infinity. But this is impossible. This doesn't happen. In reality, it goes back to zero again. When it goes to short enough wavelengths, it goes to zero again. Actually, as a function of temperature, 3000 K blackbody is something like this, and this peak goes to shorter wavelengths as the temperature goes higher and higher, but never to the infinity at the shortest wavelengths. So this is a problem. In classical physics, we cannot explain this. So the Planck, in 1900 year, Max Planck resolved this UV catastrophe with a new formula for the wavelength distribution of radiated energy. This is called Planck formula. So the radiance is 2 pi hc square lambda to the power 5 ehc divided by lambda kt minus 1. And here h is the Planck constant. Planck's formula shows radiance peaking and then declining towards zero at a short wavelength, in agreement with the experimental results. Planck's work implies that the energy of the vibrating molecules emitting the radiation must come in multiples of fundamental unit, hf. So energy will be n times hf. N is like 0, 1, 2. Here f is a vibration frequency, and h is 6 times 10 to the minus 34 is Planck's constant, a new constant that quantifies a fundamental graininess of physical reality at small scales. So, if you look at the equation, say, so the radiance, say wavelength gets longer here, lambda gets larger, right? So the radiance goes down, just like in a previous picture. Long wavelength radiation gets smaller at a certain temperature. But also, if you go to shorter wavelengths here, this part gets larger, right? Because lambda is the bottom, so this part gets larger. So if you go to short enough wavelengths, this radiance is going to go down too. It's in agreement with the experimental result. And at a certain wavelength, when this and then this is minimum, the radiance is going to peak. And that wavelength depends on this T, temperature. Depending on temperature, at certain wavelength, this radiation, black body radiation peaks. So Planck's formula can explain this black body radiation. Okay? The photoelectronic effect. The photoelectronic effect is the ejection of electrons from a metal surface when light shines on a surface. So this is the effect when the light shines. So there's a metal, and then light shines, and electron pops out. This is called photoelectronic effect. But classical physics predict that it should take some time before the electrons absorb enough energy and to be ejected. The electron's energy should depend on the light's intensity. The stronger the light, electron's energy should be higher. The color of the light shouldn't matter. So that's classical views. But in experiments, electrons are ejected immediately. When light comes, electrons ejected immediately. Electron energy is independent of light intensity. And electron energy depends on color. In other words, wavelengths. With no electron ejected for very much longer than some maximum value that depends on the metal. So what's going on? Again, classical physics has a problem here. Let's look at this figure. So so here's the circuit, and the light comes in, and then electron is ejected. So that's called photoelectronic effect. In reality, if you measure, then it looks like this. The stopping potential, this is stopping potential, indicate the maximum electron energy, which is independent of intensity. So, of course, if you increase the voltage, then the current goes up, but there's a maximum energy, maximum electron energy, and then below this, if the light is weaker than this, then nothing comes out. The electrons do not come out, and the current will be zero. How do we explain it? Then this is Einstein resolved this issue in 1905. So this is the year of miracle. Einstein wrote 4 papers here, including special relativity, Brown motion, and then this photoelectronic effect. And then 2 of them got Nobel Prize later. Actually, 3 of them are worth Nobel Prize, I believe. Okay, then Einstein's one of the paper in this miracle year explained the photoelectronic effect. Einstein suggested that the light energy comes in particle-like bundles called quanta or photons. The energy of a single photon is given by E equal hf, with h is the Planck constant, right? F is the frequency. And the energy is quantized. The more intense the light, the more photons comes off, but the energy of each photon is unrelated to the light intensity. Each material has minimum energy required to eject an electron, which is called the work function phi. The electrons emerge with maximum kinetic energy given by Kmax equal hf minus phi. Kmax depends only on the photon energy but not on its intensity. So each materials have work function. For example, silver it's 4 electron volt, silicon it's also 4 electron volt, copper 4 electron volt, cesium 2 electron volt. And unless this photon's energy is greater than this, the electron does not come out. The light cannot make the electron come out. There's a minimum energy that is work function. And then the photon's energy will be electron's energy is photon's energy minus this work function. That's how it works. This is what Einstein proposed in 1905. This means the wave-particle duality. Electromagnetic wave energy is quantized in the same way as atomic vibrations in Planck's theory of black body radiation. Since f lambda equals c, speed of the light, electromagnetic waves, the quantization condition can also be written equal hc divided lambda. Okay, this is one also hf is hc divided lambda, right? Einstein's insight shows that light has both particle-like and wave-like aspects. This is one instance of the wave-particle duality, which plays a central role in quantum physics. Einstein's 1921 Nobel Prize was awarded primarily for the photon hypothesis rather than for relativity. The Compton effect. Classical physics predict that an electron should respond to electromagnetic waves by oscillating at the same frequency as the waves, and then re-radiating the energy absorbed from the wave. In fact, the outgoing radiation is at a lower frequency and longer wavelengths. The electromagnetic radiation interacts with electrons as though the radiation consisted of particles that undergo elastic collisions with electrons. This phenomenon, first observed in 1923, gives clear evidence for photons. So let's look at figures. So in classical view, electrons oscillate and re-radiate at wave frequency. So incoming wave and oscillate, and outgoing wave with the same wavelengths. This is classical view, because waves comes and oscillates, the same oscillation, right? This is classical view, but in reality it's not. So photon, here's photon, this is light, but it comes in and as if it collides with electron and then losing energy and emerging with longer wavelength. So it loses energy because by hitting the electron and then loses energy and it comes out with longer wavelengths. And the electron is not sitting there anymore because it was hit. It gets the velocity, recoiling. So this is a quantum physics more modern view. So as you notice, this doesn't look like a wave, right? This looks like a particle hitting particle. If your particle hit particle, then it pushes the other particle away, and then this one's momentum gets slower, velocity gets slower, right? See, like this. This happens for the light. So remember, this is not a particle, but it was a light. But the light behaves like that, like a particle. So that's how the light behaves both in a wave and then both as a particle. That's why it's called photon, like a particle. And then this is the wave-particle duality. Light has two natures. as a wave and as a particle. Compton shift. We can understand a Compton effect by treating the interaction as an elastic collision between the incident photon and stationary electron. So Compton effect, we can understand it if we treat the light not as a wave but as a particle called photon and electron and an elastic collision. Then we can understand this Compton effect. The Compton shift, the change from the photon's original wavelength, is given by this equation. See, lambda minus original wavelength is 8 divided mc 1 minus cosine theta. Cosine theta is the angle that photon's gonna fly away, this theta. The Compton wavelength of electron is 8 divided mc, something like this, 0.00243. Compton scattering towards gamma rays is widely used technique for studying the structure of matter. So let's look at this figure. So if you look at this figure, the Compton scattering, if it's say the 45 degrees, the wavelength you can see. So this peak, the left peak is the original peak. The photon not hitting the electron, right? So it's at the original wavelength. But you can see the peak, right? Peak here, second peak here. That is the photon that hit the electron and then scattered. Then the point is the wavelength is longer than original one. Photon lost energy because energy went to electron, to hitting the electron, hitting away the electron. And this, of course, depends on the angle, how this the light was scattered. It might be scattered wide angle. When it comes wide angle, when it comes a small angle, and then that's the term here in cosine theta. So 45 degrees, small shift, but say 90 degrees, larger shift, 135 degrees, even larger shift, depending on putting values on this equation. And this can explain the phenomena. This is so this experiment was done by the Arthur Hawley Compton in 1923. So this is called Compton shift, Compton effect. And the last part, this Compton scattering with gamma rays is widely used technique for studying the structure of matter. So if there's a matter, we don't know the structure, and then we shoot the gamma ray and then see how it is scattered like this. Then observe this scattered light or reflected light, and then we know the structure of the matter. Okay, atoms and atomic spectra. Classical electromagnetism says that electrons orbiting atomic nucleus should radiate away their energy and spiral quickly into the nucleus. The very existence of atom is at odds with classical physics. Because, if there's an atom and electrons are orbiting around the atom, then electrons' energy should radiate away and electrons should spiral into the nucleus, right? But our atoms do not collapse that way, do not go away. It's just stable electrons orbiting the nucleus. So the very existence of atom is at odds with classical physics. Then how do we explain? Isolated atoms like those in diffuse gas give off only discrete colors which appear as spectral lines when the light is analyzed spectroscopically. In 1984, Johann Balmer found an empirical formula for the wavelengths of the first four lines in the visible spectra of hydrogen. So which is described in this equation. So lambda, inverse of lambda is n equals 3, 4, 5, 6. Where this RH is a constant, Rydberg constant, for hydrogen. And these are called Balmer lines because Johann Balmer found it. And the classical physics offers no explanation for the existence of spectral lines. So the Bohr in 1913, Niels Bohr proposed a model to explain the existence of atoms and their spectra. So this is called Bohr model. In Bohr atom, only certain orbits are allowed for the electrons orbiting the nucleus. The allowed orbits are those which the angular momentum is an integer multiple of h. H square is h divided by 2 pi. This is Planck's constant divided by 2 pi. And then Bohr's condition is NBR equals NH. This results in quantization of orbital radius and energy. So here is energy, here m is integer, right? So only certain orbits are allowed, n equal 1, 2, 3, 4. Not like 1.5, 1.3, 1.2, 2.1. These orbits are not allowed. So this is how it is quantized. An electron jumping from higher to lower orbit gives off a photon whose energy is equal to the difference in energy of the orbits. So this comes into spectral line. An electron in a lower orbit can absorb a photon of the light energy and jump to a higher orbit. So this explains the spectral lines of hydrogen, Bohr series. In the Bohr model of hydrogen, the allowed energies are something like this. This is from the previous equation and putting electron, right? Where A0 is the Bohr radius, it's 0.0529 nanometers, so it's very small radius. The wavelengths of spectral lines of hydrogen shown in energy level diagram followed from the energies associated with rate transitions among energy levels. So Lyman, so there are corresponding n2 equal 1, 2, 3, and then with n1 equal 1 to 3, they are series. So for example, here 3 series are written. Lyman series, shortest wavelength, Balmer series, next one, optical light, Paschen series, near infrared. And then if you put, for example, Lyman series n2 equal 1, you put it 1, and n1 equal 1, 2, 3, and there's a Lyman alpha, beta, gamma, delta. And then when photons goes up and down between these orbits, the light corresponding to the energy difference are emitted or absorbed. When the light is absorbed, photon gets energy and it pops up. When photon goes down, then the corresponding energy to the difference of these orbits will be emitted. So that's why the light emitted by hydrogen is always at the same wavelengths. These spectral lines corresponding to the energy difference between these lines. And then so these wavelengths corresponding to the energy difference is written down here. So 660 nanometer. This is optical light, so we can see it with eyes. So Balmer series we can see with our eyes because it's optical light. Lyman series are ultraviolet light, so shorter wavelength. Paschen series, you can see this is 1 micron, so almost 2 micron, so it's near infrared, so we cannot see it. Matter waves. Light has a dual nature, both particle and waves. In 1923, Louis du Broglie suggested the same should be true for matter. The wavelength of the waves associated with a particle of momentum p is lambda equal h divided p. Wave phenomena involving matter are often only noticeable for very small objects or very low temperatures, means low p momentum. Du Broglie's hypothesis was confirmed by observation of diffraction in electron beams. Matter waves explain the quantization of Bohr's atomic orbits, which requires standing wave to fit in the orbit. So if you look at diffraction pattern produced by beam of electrons, so remember this is electrons, but then diffraction has patterns, right? Because only because these are particle, but there's an interference. So only certain part its diffraction pattern is shown. And around electron orbits in hydrogen produce standing waves. So there's also certain orbits allowed for electron around the hydrogen. Say n equals 3 orbits, and then the other one is not allowed because this orbit needs to be a standing orbit. Okay. The uncertainty principle. The quantization of matter and energy implies you cannot simultaneously measure the position and momentum of a particle with perfect accuracy. This is called Heisenberg uncertainty principle that requires the product of the uncertainties in these quantities exceed the Planck constant. So in this case, the uncertainty of the momentum times uncertainty of the position can need to be greater than this Planck constant divided by 2 pi. It cannot so accurate as to be smaller than Planck constant. Remember, Planck constant is a very small number, so this only is all true at a very microscopic scale. Therefore, it is not possible to determine both the position and momentum of a particle simultaneously, and the concept of a precise particle trajectory is meaningless in quantum physics because it's by nature it's uncertain. The strict determinism of the Newtonian mechanics is replaced with a probabilistic description of particle behavior. The energy-time uncertainty relates the measurement of the energy of a system at the time that it remains at the energy. So in terms of energy and time, energy uncertainty times time uncertainty needs to be again greater than Planck constant. You cannot determine the time or energy at a greater accuracy than this. This is called Heisenberg uncertainty principle. So how do we understand the uncertainty principle? Heisenberg's quantum microscope thought experiment illustrates how the dual nature of the light makes it impossible to measure an electron's position or velocity without altering the other quantity. Let's look at the figure. So here's an electron, and then we want to observe this electron. But to observe this electron, we need to emit the light, and then we can only see the light, reflected light, right? But the moment you emit the light, and then light hit the electron, the light can hit the electron and then move the electron. Electron get the momentum and it moves. So by the time the light comes back to the eye or observation of human, the electron was already moved by the observation. So there will be certain uncertainty. This is called Heisenberg's uncertainty principle. Okay, the wave nature of matter ultimately imposes a trade-off. The more we know about a particle position, the less we know of its momentum, and vice versa. So, if you use for example, let's look at this. Then, if you use a wide slit like figure A, then position is uncertain, right? But in vertical momentum, which way it is, we can determine more precisely. But okay, we want to measure the position accurately and then make this slit smaller. Then okay, the slit is smaller, so the position is more accurate. But the momentum, because if you make the slit smaller, then light is reflected this one or this way, so the momentum becomes uncertain. So this is uncertainty principle. Complementarity. How can matter and light both be both wave and particle? Bohr answered with his complementary principle. Wave and particle aspects are complementary. Both are needed for full description of reality. They are not contradictory because nature never manifests both at once. do an experiment on wave behavior and you find the wave aspects. For example, pass light or matter through a two-slit system and you get an interference pattern. So this is wave features, right? Do an experiment on particle behavior and you'll find the particle aspect. For example, photoelectronic and Compton effect. So these are particle behavior. So the light and matter both have both aspects, wave and particle. That's very interesting. So here's a summary of today. Quantum physics developed out of contradictions between classical physics and experiments. The ultraviolet catastrophe, this Planck software, the photoelectronic effect, Einstein explained. Atoms and atomic spectra, Bohr explained it. Resolution in these cases involves quantization with Planck constant h, describing a fundamental grayness at small scale. Both matter and light exhibit both wave and particle aspects. This leads to the uncertainty principle. But there's no contradiction as described by the complementary principle. Both are the nature of the reality. Okay, so that's end of the lecture today. Next time we're gonna take a deeper look at quantum mechanics. So more interesting stuff are coming up. So see you next time. Bye bye.